Yo, it's Quan Penguino. Today we're going to do something a little different. We're going to take a break from the QFT series, and I'm going to start doing a little side series on group theory using the textbook Lie Algebras and Particle Physics by Howard Georgi. So today is just going to be basically the basics, and we're going to do some hands-on exercises using the cyclic group Z3. I kind of wanted to do this video because in chapter 3 of Peskin and Schroeder, they start going kind of crazy with Lie Algebras. So kind of for myself and for you guys, I thought it'd be a good idea to start going into that group theory textbook a little bit. So we're going to start a bit basic and discuss 4 attributes that define a group. First, we got the closed property, which means that if you multiply any two of the group's elements, you get an element that's still in the group. Then we have the associative property, which is just like the one in normal multiplication, where you can change the order in which you multiply different group elements in a sequence, and you still get the same result at the end. Then there is the existence of an identity element, which means that any group element multiplied by the identity element gives you the same group element. And finally, we have the existence of an inverse, which means that every element in the group has an inverse, so that if you multiply the element times its inverse, you get the identity. Before going into a concrete example of a group, I wanted to introduce another concept, which are representations. Representation of a group is a homomorphism that maps each element of the group onto a set of linear operators that act on some vector space V. The key part of this definition is that the linear operators are preserving the way the group operates, which kind of points back towards the fact that D is a homomorphism. So representations have 2 key properties. One is the identity, which is that the linear operator acting on the identity of your group also maps to the identity of the vector space which you are in. The next property is what I like to call the preservation of structure, and honestly the best definition for this is in the textbook itself. It says that the group multiplication law is mapped onto the natural multiplication in the linear space on which the linear operators act. So the group that we'll be working with for the rest of this video is the Z3 cyclic group. We can characterize this group using a multiplication table, which shows how each of the 3 elements in the group act on each other. For example, E, the identity, leaves every element unchanged. A and B are inverses, so A acting on B or B acting on A gives you the identity. And then consecutive applications of A on A or B on B give you the element B or A respectively. While we're at it, we can add some more definitions into the mix. The Z3 cyclic group is finite and of order 3 since it only has 3 elements, and it's also abelian as the multiplication law is commutative. For example, A times B is the same as B times A, and the identity times A or B is the same as A or B times the identity. So now we're going to start getting a bit hands-on, so I suggest you buckle up. We'll start slow with the 1D representation of Z3. Here, the homomorphism D is mapping the elements of our group onto the complex plane. We see that the representations of A and B are inverses as e to the 2 pi I over 3 times e to the 4 pi over 3 just gives you e to the 2 pi I, which is equal to 1, which is the identity in this context. Another way of thinking about this is that the representation of the identity is a 0-degree rotation, the representation of A is a 120-degree rotation, and the representation of B is a 240-degree rotation. That is why Z3 is called the cyclic group. We can take this one step further and identify the 2D representation of Z3 by having this homomorphism map the elements of our group to the 2x2 complex plane. And then we can go through the same exercise as we did for the 1D representation. We multiply the representations of A and B times each other, and see it gives us just e to the 2 pi along the main diagonal, which is just 1 returning the identity matrix. We can do the same thing for A acting consecutively on itself, and see that dA times dA just gives you dB. So if you've been following along, you'd probably guess that the next representation we're going to look at is going to be in 3D, and you'd be correct. This representation is a little bit special as it's the regular representation. What makes it the quote-unquote regular representation is the fact that each element of G is mapped onto a set of permutation matrices. The form of these permutation matrices is given below, where we map each of E, A, and B to E1, E2, and E3 respectively. In fact, this form lets us find the regular representation analytically. So as an example, we can write out the whole matrix for the regular representation of the identity in terms of all these matrix elements. Basically what happens is that D of E will act on the ket, and then if the bra is then equal to D of E times the ket, then it'll go to 1, but if they're not equal, it'll just go to 0. Since in this example the identity leaves the ket unchanged, the only values that are going to be 1 are the ones along the main diagonal where the bra and the ket are already the same. We can derive these same matrices for the case where we have D of A and D of B, but I'm just going to quickly flash these on the screen and you guys can pause and take a look if you want some more time to understand. But in the end, after deriving all three matrices, we have the regular representation of Z3 comprised by these three matrix definitions. However, not all representations are built the same. In fact, there are three main types we're going to cover in this video. First is irreducible, followed by completely reducible, and then reducible. Looking at irreducible representations first, what makes them unique is that you cannot find a subspace to map the representation to that is not the null space or the whole vector space itself. In fact, there's a theorem that states that every irreducible representation of a finite abelian group is one-dimensional. Now, I won't prove that in this video for the sake of time, but that is why all the following representations are all 1D, because the cyclic group Z3 is finite and abelian. So the first irreducible representation is just a trivial representation where we map every element to 1. This of course still preserves the group structure, as A times B still gives you E, E times A still gives you A times A still gives you B, etc., since everything is literally the same, everything's just 1. The first non-trivial irreducible representation should look very familiar, as it's the first representation that I presented in this video on the slide with a plot of a circle. And then finally, the second non-trivial irreducible representation is very similar to the last one, except the mappings of A and B are flipped. So essentially, instead of mapping A to the 120-degree rotation, you're mapping A to the 240-degree rotation. This works and still preserves the group structure since A and B are inverses, so switching them around doesn't change anything. Now we're going to move towards completely reducible representations. The definition of these are that the representation D can be written in block diagonal form as a direct sum of different irreducible representations. So this is shown in the matrix below, where the elements along the main diagonal are the linear operators mapping group elements in different irreducible representations. So we were actually just talking about three different irreducible representations for Z3, and we can use these three to derive a completely reducible representation of Z3. We can start simple with the identity matrix, and we just take each of the linear operators corresponding to the identity element in each of our three irreducible representations and map them to positions 1, 2, and 3 along the main diagonal of the completely reducible representation. Of course, by construction, this just yields the 3x3 identity matrix. We can derive the representation matrix for A by performing the same process, and we get along the main diagonal 1 omega and omega squared. And then we can do the same thing for B, getting the slightly different but still very similar 1 omega squared omega along the main diagonal. These three block diagonal matrices form the completely reducible representation of Z3. Now we reach our final type of representation, the reducible representation, and our final example for today's video. So you can call a representation D a reducible representation if there exists a non-trivial subspace W, which is a subset of V, with two main properties. First, it's that W is invariant under the action of G. What this means is that for every element in G, your representation of that element times any vector in the subspace W remains in that subspace. And the other property is that this subspace W can neither be the zero subspace or the entire space V. So to start finding a reducible representation of Z3, we're going to define a projection matrix P, which is just a 3x3 matrix in R3 that has all entries equal to 1 and a normalization factor of 1/3 on the outside, which will come in handy later. We see that applying the projection matrix onto an arbitrary column vector in R3 gives us an outputted column vector whose entries are each the sum of the original entries of the original vector. If you were to apply the projection matrix again onto this column vector, you'd see that you'd just get the same vector over and over again. This property is actually called idempotence. In addition, we see that the condition that W is neither the zero subspace nor the entire space V is satisfied, as the subspace that we've projected onto is the one spanned by the column vector 1, 1, 1 in R3. So we don't actually have to find a reducible representation, we already have one, and that's actually the regular representation that was presented earlier on in this video. To prove that the regular representation is a reducible representation, we just need to show that the subspace that we've projected onto is invariant under the action of the group, which means that once we apply each of the matrices from the regular representation, we still get back an element that's in the projected subspace. So as always, applying the identity is trivial, and it just gives us back PV. So this one holds so far. We can do the same thing with A, and we see we still get back P times V. And surprise, surprise, we do the same thing with B, and we see that we also get back P times V. In fact, what we notice is that the regular representation is acting like the trivial representation in this subspace, as applying any of the matrices that are part of this representation just is equivalent to applying the identity 1. In addition, we've shown that W is invariant under the action of G, as applying any of these linear operators just gives us the same vector each time, meaning that the operations are closed under this vector subspace W. So that's enough to prove that the regular representation is actually a reducible representation on Z3. Unfortunately, that brings us to the end of today's video. I hope you all enjoyed. Hopefully I'll make some more group theory videos like this, as I think it's good to study both group theory and QFT at the same time, since they're pretty much intertwined. But yeah, thanks for watching to the end, and I'll see you guys in the next video. Peace.